Hello and welcome to the spoken tutorial on solving linear programming problems with two index variables in Scilab. In this tutorial, we will learn how to solve a linear programming problem having variables with two indices in Scilab, use Karmarkar function, use transportation problem as an example of linear programming. In order to understand this tutorial, you should have gone through the spoken tutorial on optimization using Karmarkar function. This tutorial is available on the spoken tutorial website. You should be familiar with linear programming and have Scilab installed on your system. In this tutorial, we will refer to linear programming as LP and transportation problem as TP. If a variable has two indices in LP, then it is called a two-index variable. For example, x 1, 2, here x has two indices 1 and 2. An example of LP with two index variables is the TP. To understand the transportation problem, we consider the following network as an example. This network has three supply nodes, plant 1, plant 2 and plant 3, two demand nodes, site S1 and site S2. We can transport goods from P1 node to S1 and S2 with transporting cost C11 and C12. Similarly, goods from P2 to S1 and S2 with transporting cost C21 and C22. Goods from P3 to S1 and S2 with transporting cost C31 and C32 respectively. The aim is to supply goods from the plants to the sites with the total minimum transportation cost. Supply nodes cannot transport more than their capacity. Note that all the demands at the site must be met. Supply capacities, demands and transportation costs are known. A cement company transports cement from plants 1, 2 and 3 to construction sites 1 and 2. The available supply at each plant is plant 1 45 tons, plant 2 60 tons and plant 3 35 tons. The demands of sites are site 1 50 tons and site 2 60 tons. The cost of transporting 1 ton of cement from each plant to each site is given in the table. Transporting cost from plant 1 to site 1 and site 2 is 3 and 2 respectively. Similarly, other plants have transporting cost. Each plant has available supply. Each site has demand. We will formulate it as LP problem and find its optimal solution. Two-index decision variable Xij is the number of tons transported from plant I to site J. Formulation of this problem is objective function minimize 3x11 plus 2x12 plus x21 plus 5x22 plus 5x31 plus 4x32. Constraints: since plant 1 cannot supply more than its capacity, therefore we have x11 plus x12 is less than or equal to 45. Similarly, for plant 2, we have x21 plus x22 is less than or equal to 60. Similarly, for plant 3, we have x31 plus x32 is less than or equal to 35. Demand at the site 1 must be met. Therefore, we have x11 plus x21 plus x31 is greater than or equal to 50. It is equivalent to minus x11 minus x21 minus x31 is less than or equal to minus 50. Both constraints are equivalent to each other. We multiplied with minus 1 to make inequality constraints in less than or equal to form for Karmarkar function. Similarly, at site 2, we have x12 plus x22 plus x32 is greater than or equal to 60. It is equivalent to minus x12 minus x22 minus x32 is less than or equal to minus 60. Xij is greater than or equal to 0. This is because transported quantity cannot be negative. I is 1, 2, 3 because we have 3 supply nodes in this example, and j is 1, 2 because we have 2 demand nodes. Karmarkar function is LP solver in Scilab. Karmarkar function solves the LP problem in the following form. Minimize C transpose X subject to AEQX is equal to BEQ, which means constraints have equality sign. AX is less than or equal to B, which means constraints with greater than or equal to sign must be multiplied by -1. LB less than or equal to X less than or equal to UB, where LB stands for lower bounds and UB stands for upper bounds on the variables. C transpose AEQ, BEQ, A, B, LB and UB are the known parameters. X is the vector of decision variables. Coming back to our example, the coefficient vector of objective function is C transpose 3, 2, 1, 5, 5, 4. This vector size will change according to the example. In our example, it contains 6 numbers. The coefficient matrix of constraints is capital A. In the first row, we have 1, 1 and rest of the variables are 0. This is because in our first constraint, only variables x11 and x12 are present and rest of the variables have 0 coefficient. Row 2 is 0, 0, 1, 1, 0, 0 because second constraint has variables x21 and x22. And row 3 is 0, 0, 0, 0, 1, 1 because third constraint has variables x31 and x32. In fourth row, we have -1, 0, -1, 0, -1, 0. This is because in our fourth constraint only variables x11, x21 and x31 are present. Fifth row is 0, -1, 0, -1, 0, -1 because fifth constraint has variables x12, x22 and x32. The vector of right hand side of constraints is B transpose 45, 60, 35, -50, -60. LB is equal to 0 for all variables as all xij are greater than or equal to 0. In our example, we do not require AEQ, BEQ and UB. I have a working example with me. I will open my opt.sce in the Scilab console. Pause this tutorial and click on the code files link below the player. This will download opt.sce file on your machine. Locate this file and open it in the Scilab console. Now resume the tutorial. In the formulation of TP, C is the coefficient vector of the objective function. Capital A is the coefficient matrix of constraints. B is the vector of right hand side of constraints. LB is the vector of the lower bounds of the constraint. Upper bound is empty vector because we do not require it in this example. Now we can call the Karmarkar function to solve TP. Each parameter in this function is explained in the spoken tutorial mentioned earlier. In TP, 4 parameters C, A, B, LB and UB will always be present and rest will be empty. This line will display XOPT value, which is the optimal solution of TP. This line will display FOPT value, which is the optimal value of TP. Now click on the execute button. After that, go back to the Scilab console to see the results. The optimal solution and optimal value are given. First value is x11, second value is x12, third value is x21, fourth value is x22, and fifth value is x31, and sixth value is x32. Note that x11 can be taken as 0 since the decimal value after 0 is floating point error. x12 can be rounded up to 45, x21 can be rounded to 50, x22 and x31 can be rounded to 0. Optimal value is 200 only, as decimal places are only floating point errors. In our example, red edges denote the non-zero variables in the optimal solution. In the optimal solution, we can transport 45 tons from plant 1 to site 2 with transportation cost 2 per ton, 50 tons from plant 2 to site 1 with transportation cost 1 per ton, 15 tons from plant 3 to site 2 with transportation cost 4 per ton. Other values of x are 0, so we do not transport goods on those paths. Thus, the minimum transportation cost to transport the goods is 200. Here is an assignment for you. Here we have 2 plants and 2 sites. Transportation cost is given in the table. Hint: formulate this problem as explained in the previous example. Please solve it using Karmarkar function and verify. The optimal value should be 520 and the optimal solution should have x12 is equal to 60, x21 is equal to 100 and all others have 0. This brings us to the end of the tutorial. Let us summarize. In this tutorial we have learned about variables with 2 indices, example of LP with 2 index variables and its input parameters. We have also learned applying Karmarkar function to solve linear transportation problem in Scilab. OR Tools series is created by the FOSSEE project, IIT Bombay. FOSSEE stands for Free and Open Source Software for Education. This project promotes the use of free and open source tools. For more details, please visit at this link. The video at this link summarizes the spoken tutorial project. Please download and watch it. The spoken tutorial team conducts workshops and gives certificates on passing online tests. For more details, please write to us. Spoken Tutorial project is funded by NMEICT MHRD Government of India. More information on this mission is available at this link. The script is created by Suraj Trivedi and this is Rahul Joshi from FOSSEE project, IIT Bombay signing off. Thanks for joining.